Hello, YouTube freaks. We're going to be going over a sigmoid because it sounds cool. And I like that. So first we have some data here supplied kindly by my professor, Fred. So it's just example data. So we want to plot a line through these three data points. You're usually gonna, or if you were gonna use like a linear, like OLS or whatever, it'll look something like that, or something straighter, maybe something like that. Kind of hard to say, but that might be correct. But that's not what we're doing now. We're doing sigmoid stuff. Okay, so we're doing. If I can just pull it up. Oh! So essentially how it works, we have our x, which is then going to help us find, we have some z here, which is equal to this. And we'll go through how we're going to find all this stuff here. It's important to note that our a, it's a sigmoid, which is equal to 1 over 1 plus e to the power of less z, which is derived by, or it's given by g of z, which is equal to e of z over e of z plus 1, which is equal to 1 over 1 plus e less z to the power of less z. And then finally, we have our prediction, which is equal to a, it says here. And I don't know if that's always going to be the case or what. Anyway, we're not going to worry too much about it. In this case, we find that our z is equal to this right here. Gives us, we do our linear regression step. Like I was saying, it's just a linear regression. It gives us this 11.6 x. And then we need to compress, this is going to compress z in between 0 and 1. So this function right here takes our z and kind of like puts it in the parameter, or in between 0 and 1, right? So a is always in between 0 and 1. And our final step is our output prediction, which is just y is equal to beta 0 plus beta 1 a. And we use our intercept. We kind of flip the sign over here. That's less 1.38 plus 2.98a. Okay? So we have to plug in the different values of x. I don't know if I want to... Nah, it's worth it. So we plug in our different values of x here. They're given to us here. So we have 1 at 0, 1 at 0.5, and then 1 at 1. Okay, so they're not arbitrary. They come from our data. So for 0, for example, we have our z here equal to 1.38 plus 11.6 times 0. I wonder what that's going to give us. And then it gives us 1.38, okay? And et cetera, et cetera, et cetera. So, again, after you find this, then you plug it into your a, 1 over 1 plus e to the power of less 1.38, which gives us 0.8. And then we plug that in to our y, negative 1.38 plus 2.98, 0.8, because this is our a, which is approximately equal to 1. And I'll just give you the others. So when x is equal to 0.5, our prediction goes to 1.6. And when x equals 1, so this is at x equals 0.5, y hat equals 1.6. And when x equals 1, y hat equals 1.6. So it kind of goes like, the new graph kind of goes like, and then it plateaus, right? So it's kind of like, goes up and then plateaus. The whistle was it plateauing. The more you know. So it's not very good. It's kind of like only going through one point and then it misses these two, but this is a if I could find it. I can't find it. It is a one hidden unit with sigmoid activation. We're going to do a 2 hidden unit with sigmoid activation, and you'll see how much more accurate that is. It's a lot more accurate, and we're going to go over some more machine learning stuff. This would be under deep learning, and we're going over some of the basics right now. So follow these videos in order, because I'm going to be kind of going through stuff in order, or at least in order so as far as my professor thinks it is, because this is how he went. He started here, and then the examples continue to get more complex and almost certainly more useful as well. So anyway, I'll catch you in the next video, which will hopefully be out a little later today. And yeah, subscribe if you want to see more.